Cool, we are live. Welcome everyone to the next episode of DATAPULSE. Today we'll be talking about the Lakehouse architecture and the analytical plane. We did a previous session on this topic 2 weeks ago with 𝗪𝗪𝗪𝗪, and we did touch a lot of the topics we'll be touching today as well. But we feel that we didn't exhaust the topic, so we wanted to extend on a few aspects that were maybe just mentioned last time in a bit more structured manner, because this time we have slides. Hopefully this will help a little bit in navigating through the plan. So my name is 𝗪𝗪𝗪𝗪𝗪𝗪, and together with 𝗪𝗸𝗏𝗪𝗏𝗪𝗏, welcome. Let's go. I'll do my best not to repeat myself, but to catch up a little bit on the context. Last time we talked about the Lakehouse architecture that answers to certain problems. Like everything in software, it didn't emerge in vacuum. It emerged as an answer to certain issues that were faced by the architecture that's dominant in the analytical plane of many organizations today. It's a two-tier architecture where we have a data lake where all of the data is ingested, but within this data lake, we might not within, but then we also have data warehouses, and data from the data lake is copied to data warehouses for high performance computations. And it works, it solves the problem, but it also introduces certain challenges that Lakehouse is an answer to. One of those is, we copy data, right? So first of all, we might have issues somewhere during copying and might need to manage the coherency between these copies. Also, copies incur cost. And copying data somewhere means it's there, and we get data silos quite often, and sometimes a vendor lock-in with a proprietary warehouse. And on top of this, this is just more complex than it can be, apparently, because this was the norm for a long time, and but right now the Lakehouse is kind of where it's at. It's already introduced in many massive organizations, and it seems to be the next generation of the analytical data architecture. And in the center of the Lakehouse are the open table formats, about which we'll be talking a lot today. But the primary idea that we see here is that data warehouse is great because it gives us huge performance benefits. But data Lakehouse tries to get these benefits without sacrificing the cost efficiency of a data lake. So it kind of decomposes the concept of a warehouse and rebuilds this in a cloud-native manner on object storage. Which one of the great benefits is that it decouples storage and compute. So storage is just object storage, same as it used to be the Parquet files, right? But now it's accessible everywhere, and whenever we need to compute something, we can just provision the compute locally, do the computations we need, and in general, we can have a single source of truth without copying the data too much. It doesn't mean that we don't copy. It means that it's possible to have this single copy now, where it wasn't feasible before that. And another huge aspect of this is the openness, the interoperability, because here you can see on the diagram, this diagram is, I think, from Hudi, but it's the one that I like the most. I've seen many different diagrams about Lakehouse, but this one kind of keeps things simple, where we have different functions, different components of the Lakehouse. And these functions can be fulfilled by many different technologies, and they are very often interoperable. You can swap one for another, and then the rest of the stack will still work. So given this short introduction to kind of set the context to what we are talking about, in the center of it, there are open table formats. The most talked about today is Iceberg, but there are many others that we want to cover. So Sachin, maybe you take over from here.
Sure. So Lakehouse is a concept which is enabled by open table formats. What are open table formats? Open table formats are the agreed upon standards. Like, how do you want to organize your table data and the metadata on the data lake or the object storage? So you have your data files, you have your metadata all sitting on the object storage. is what and how do you interact with them, like whenever you want to add anything, delete anything, how do the metadata changes look like, and correspondingly what data files gets changed, is what OpenTable format specifies as standards. As Ian already has mentioned, there are like three major competitors right now in this field: Iceberg, Lake, and Hudi. Paimon is slowly and very aggressively catching up. And we have a dedicated slide because we are very interested about Paimon. And so yeah, so these are the few major pillars that we'll be talking about across our slides in this particular presentation. The major benefits that we get from this is schema enforcement evolution. One format does better than the other, and like vice versa, because they have different ways to operate on that. So let's say you have these fields which are represented as field IDs in specific to Iceberg, but not in Delta Lake. Hence, for Iceberg, add, drop, rename, reorder, change column, everything is just metadata changes. So there are two sets. One is metadata, one is data file. The less you interact with data file, the faster you do the processing, right? So Iceberg just interact with the metadata file, do not do anything with the data file for these changes, whereas Delta Lake has to do it. You can enable certain parameters to not to do it, but then that has its own cons and things like that. That's schema enforcement part, which was very severely missing on the Delta Lake setup. Then we have this ACID transactions, multiple concurrent writers trying to commit their own writes, right? And then let the last writer win. That was the problem with the Delta Lake. Data Lake. I keep on confusing between these terms, Data Lake and Delta Lake. So Data Lake, right? Which is solved by your Lakehouse format, where you have like multiple concurrent writers trying to commit their rights, and the last writer not always win. It's again the whole refresh, so that the previous writer which has made the changes also got accumulated in the last writer update. So those are the things that we'll be also discussing. But like on a high level, these are the major benefits that they provide. We can, like, while talking about OTS, we can also talk about how they are useful in different industries. So if you're someone who is working in BI analytics, how is it useful for you versus if you're working in data science versus if you're working in streaming, right? So for your BI analytics, earlier in the data lake era, what you would be having is you're just left at the mercy of your Parquet footers. So Parquet footers hold the min and max of your specific columns, and your query, whenever it just do the query, it just check the Parquet footer, and depending upon that, it will fetch all the data files. And then there's also partitioning you can do. So, but the partitioning is again bottleneck that you cannot have it on the more granular column and stuff like that. So that was there. But now with this Lakehouse, we have this whole tree-like structure, which provides you the faster pruning or more aggressive pruning, because at each level of this tree-like structure of metadata, you'll get the benefit of pruning. Then again, like as Ian has already mentioned, for all the different tools like your Flink, Iceberg, your Flink, Spark, Trino, all can talk to the same single copy of the data, right? So hence the less data movement. So single copy is not just beneficial BI analytics, but is also very useful for your governance and frugal choices. For data
science, easier to govern data when you know where it's at, right?
That's right. Exactly, and that's like all these benefits are there available for your data science team. But one of the major standout thing is if you want to do time travel. So what I mean by time travel, and this is almost all the Lakehouse provides. What do they do in that? So they provide you the facility to check the snapshot, not just as it looks today, but how it looked yesterday, a day before yesterday. So you might need to train your model on different snapshots, how my data looks today, but then how it looked yesterday, how it looked day before yesterday. So all those time travel you can do for your model training. And for streaming a real-time application, there's a shared schema. So we will be talking about TableFlow and all those things of unifying operational and analytics plane. But then there's a single schema across your operational plane and your analytical plane. And then interoperability, as already Ian has mentioned. So this is a very big thing for streaming and real-time application. And because it's single copy, less data movement you're doing for different tools, and it's also governance friendly, and it's a frugal choice. You're not like having a lot of data movement and stuff like that. Yeah. So this is another thing that you would want to talk about. So what is canonical set of files? Okay, so canonical set of files is your data file or delete files. Data file actually the actual data, and the delete files which Iceberg actually maintains to identify which rows that it needs to delete. So understanding how these different Lakehouse formats vary in this particular school of thoughts is will help you to decide which one to go with for a specific workload. So there are two school of thoughts originally. One is log of delta, the other one is log of snapshots. The log of deltas is and the example for that is your Delta Lake or Apache Hudi. So let's take Delta Lake. In Delta Lake, for the log of deltas, you will have like _delta_log folder. Any changes that you do into your data file will get reflected as an add if you have added, delete if you have deleted into your _delta_log. It's simple JSON files. So it's very fast for a writer to just commit a JSON file for your whatever incremental changes that you're doing. But then for your reader, it has to process all the changes that it has been done by the writer to get the actual state of the data. That's not very reader friendly, but very writer friendly. So what the optimization that they do? The optimization at Delta Lake is creating a snapshot, checkpointing, basically not snapshot, checkpointing of the delta log till a point, and then again a new incremental delta logs will keep on getting written. So your reader do not need to scan all the files. Instead, it will just scan the checkpoint and then the new delta that has been recorded. For Hudi, it is instant versus a specific table. So if you just want to query a specific state of the table right now, it's a specific table that you can just query and get the data. But if you want to do time travel, you have to interact with the instance and timeline that they provide, similar to the Delta Lake concepts of recording the logs. This is very different to the log of snapshots. Like Apache Paimon and Iceberg follows this. What happens is this is for any changes, you will create the whole tree of metadata. For any incremental changes or insert, update, or delete, whatever, it will create a whole metadata structure for that: snapshot, metadata files, manifest list, manifest files, and then the data file that you have. It's a little taxing at the writer side, but it's very reader friendly. And Iceberg and Paimon, Iceberg specifically has been dominating on this field of reader friendly type of operations. Hence, they have taken this approach. But then if you have this write heavy approaches, we just want to commit the writes and stuff like that, log of delta is the approach. But then Iceberg is improving in this direction, where that we'll discuss in the V3 version when we'll talk about more on this.
Yeah, but then when I saw some cost breakdown of how it works in analytics, most of the costs come from reads, right? The data is written much less frequently than it's read. So I guess this could be one of the reasons where Iceberg got an edge.
Yep, definitely. And that was like in our first discussion, we discussed this. At analytical side, we are not that much time sensitive. So we do things on batches as compared to the operational field, where it is very time sensitive stuff. Again, so we understood how do we represent a data file and delete files, and the pros and cons of each of them. Then we also need to understand how they handle your insert, update, deletes to the specific tables. So again, there are two school of thoughts. The one school of thought is supporting primary key or LSM based structure, and the other one is do not support primary key, not LSM based structure. So you have Hudi and Paimon, and Hudi specifically. So Hudi was there in your log of deltas as well as it is in primary key support, right? So what it basically provides you is, so for Hudi, for each primary key you will have file groups. For Paimon, for each primary key you will have buckets. And like Iceberg and Delta Lake do not support primary key. What's the problem with that not supporting primary key? So let's consider as upsaltable load. So you want to upsalt a specific set of records into already existing a big table, right? So in upsaltable load, you got this new record that you want to upsalt, which is let's say 100 of rows, and then you have very big petabytes of size of table that you want to upsalt into it. What you want to avoid is not reading this whole big petabytes of table, right? But because it do not support the primary key, there is no way for your engine to know which is that particular file or position where I need to update these files to. To do that, it has to scan whole big table, both of the big tables, like the smaller and the bigger tables, to find out the position that where it need to make the upsert, and accordingly create a delete files or data files to support that, right? Because it's natively supported in Hudi and Paimon, you don't have to do all those things. You just provide that, you'll get the primary key, from the primary key, you'll get to that file group or buckets, and that will just give you the opportunity to just not read that in the next read. So you do not need any delete file concept with your Hudis and Paimons. Iceberg is improving aggressively in this direction, and that we will talk when we'll talk about V3. But that's where we are at right now. Again, so just skipping this, like quickly walking this up. So we have two types of streaming. One is when you're just appending the data. The other one is streaming when you want to create the exact mirror replica of your actual source database. So you want to do update and delete. So append is upsert friend. You do not have any upserts. Whereas streaming data with updates and delete is where you want to create an exact mirror replica of your source table. So that's like two of the streaming ingestion pattern that we can deal with this what we have discussed just before.
Yeah, and it's especially important for the operational world where efficient retrieval by key, and in general you operate more or less on single objects, less on large data sets. And the very interesting answer to this problem is Apache Paimon, and I will be explaining Paimon for the first time. I don't understand it fully 100% yet, but I'll do my best to transfer what I understand about it. The core idea is that you want to optimize for fast writes and you want to optimize for retrieval by key without sacrificing this analytical query performance. And Apache Paimon has a non-PK table, so just append only table, but the PK table one is the very interesting innovation to me. How it works is that there is an, I think, in-memory structure, which is a mem table that has very efficient reads. So you can append to data, and this is partitioned, so you get buckets that you can write to in parallel. And then after the mem table gets filled, what is created out of this is a sorted run. So the data in the mem table gets compacted so that you get one record per key. This data is sorted by key, and you get an ordered set, ordered sorted run that you put on the leaf of your LSM tree. And on top of this, you not only get it sorted, but you get a summary of the primary keys in this set, in this run. So you can get very efficient retrieval even if you want to retrieve a single object. It's not for single object. This is for analytics, but yeah. And on top of this, when you get multiple records with the same key, there are multiple merge engines supported. You get the default one. It's called the duplicate, where you overwrite all of the previous entries under the previous key, which is intuitive, right? The new record under this key, this is a table, yeah, we overwrite. But you can also do partial updates, where, for example, if you have a table with 30 different fields, but you want to update only 3 of them, you publish or add a record with only 3 fields, the others are null. And then if the table is configured to do partial updates, you only update these 3 fields. You can also do aggregations, so summing up, counting, and so on, basically computations based on the current state of the record. And then there is also something interesting for consistency, which is only the first row, right? So one of the activities that you sometimes need to do is deduplicate. You know that you can, the record is immutable, but you might get multiple copies of the same record. So with the first row merge engine, you just take, yeah, we already have this record. We don't need to compute further. Yeah, and what's very interesting about this is that Paimon is Iceberg compatible if you configure it this way. So not write compatible. Iceberg compatible writers, like they need to understand Paimon. But the data that's in Paimon, it can be read by any Iceberg compatible engine because this is just not just, but it's building on top of the Iceberg idea of metadata, data, and summaries and so on. This is stuff that I found out today. I was curious. I've read about Paimon a lot in the past months, but today I saw some slides from Think Forward Asia about where it is used in production, and apparently Alibaba, this is where I think it originated, but also TikTok and Xiaomi and many other massive global organizations are using Paimon in production already. So I had this question in my mind. Very interesting. How is the adoption? And seems like the adoption is progressing rather quickly. So I'm really looking forward to seeing more and more Paimon in news, in the content I read. But Paimon is just one answer to the problem of how do we unify, one proposition on how to solve the problem of unification, right? Fluss is another solution that's connected to it. I won't go into in depth into it. It's also an Apache project, also originated in 𝗪𝗵𝗵𝗵. But there is also something that we've talked about a lot already on DATAPULSE, the table topic abstraction. This is an approach that's implemented by many different Kafka vendors or Kafka compatible brokers. Where you have data in your topic, you have a connected Iceberg table or Delta Lake table connected to it. And then you have a single schema, and you have an engine that moves data from your Kafka topic to Iceberg all the time. This way you can have this efficient analytical query performance connected with the very low latency of Kafka. On top of this, not that long ago, Confluent announced snapshot queries, which is a feature that allows you to execute Flink SQL queries that give you the aggregated state from at a given point in time that does analytical query on Iceberg, but also from the last 2 minutes, however you configure it. The last 2 minutes that's not moved to Iceberg yet, scan the topic. And that's something that I expect to be adopted by others as well. AutoMQ does table topic that's open source. That's pretty interesting because as far as I know, this is the first significant table topic open source implementation. BuffStream does something really cool. They allow you to write to Iceberg from their Kafka compatible broker. But also what's really unique right now, I guess this will be implemented more and more, is they allow you to, this broker is able to serve Kafka format from the Iceberg table, right? So if you want to read some old data by your Kafka consumers, you can just query the Iceberg table that's managed by BuffStream directly. So that's table topic. I'm very bullish on this. I think that this is the Iceberg and Kafka are two extremely widely adopted formats right now. But if you don't want to have this complexity of two different systems that are used by many different applications on both sides, you might do something that 𝗪𝗏 does, which is direct CDC into Iceberg. CDC is a concept that most of us are probably familiar with from Debezium and Kafka, where Debezium is a CDC connector that moves data from a database into Kafka, and then this data can be streamed to wherever you want. 𝗪𝗏 does this a little bit differently because they don't have this Kafka in the middle, and it's an open source solution that moves data from a source to a destination without ETL, without much complexity. And there are also, of course, other ways to do this with a bit more heavyweight tools like Flink or Spark. Like you can get CDC ingestion in Flink and many other connectors. But this is still not as integrated, not as unified. So what I like here is the extreme simplicity of it. It's not a fit for that many use cases because it introduces coupling between your database and your Iceberg table, which means that frequent schema evolution might be a problem. You might introduce a component in the middle like Kafka for stability. But it definitely is a great way, for example, with legacy applications to just have the data that's in your database, to have it accessible almost immediately in your whole data platform.
I think object storage is becoming the default storage, and Iceberg is becoming a default lakehouse over that specific object storage in that way.
Yeah, definitely looks like it. Yeah, so about Iceberg, I know that you have some thoughts and news about this, because this is a pretty challenging topic. Like what Iceberg is even capable of, and how do you manage your tens of tables sometimes, and with each of these tables tons of data.
Definitely, yeah. So as we already discussed in our previous slides, that there are some hiccups for Iceberg when you have like streaming type of ingestion workloads. And the major issue with that is scanning the target table, creating a lot of delete files, stuff like that. So per data file, there will be like lot of delete files, and the reader or the reader engine has to compact all the data file, the delete files to make sense out of it, right? Until unless you do the compaction regularly, right? So until the compaction is done, it's the whole responsibility of a reader engine to make sense out of that data. So that this created this term of deletion vector that was already available delta, but they just created this. With that, for one data file, there will be only one delete file. So any changes that you want to delete or update, so those for that particular data file will get recorded into that specific delete file. That's one part. And the other part is the delete file is stored in a Puffle object storage in that format. So it's natively understood by your engine. So you do not also need to deserialize that. That was the case with V2. So it's one part of that is streaming workload can create a lot of files. The delete file will not be that much prominent, and the reader will have a little relaxed life. But then, because it do not support native primary key yet, and there's a big yet there, because I think that there's a direction in which they are going. But because they do not support it yet, hence you have to still read the whole bigger table to get that specific positions. That's one part. V3 is not just stopping there. It also has like very cool feature of row level lineage. So earlier, either you do compaction or you do have like copy on write type of workloads. Your row will keep on moving from one file to other file, and then there is no way for your rows to get a specific row ID till V2. In V3, you have that, and that's a very big enabler of your incremental querying. So now your query engine can have that row ID recorded and can also have the sequence number that I have read for the specific row ID till sequence number 10. Until unless I see anything for this row ID greater than 10, I will not read that. Hence, it's very incremental friendly. So these are more on the streaming workload enablement and incremental part of that. So making a reader's life much more easier. The other part is on the variant data type. So it's also not just stopping there, but also making your Iceberg much more data type rich. So in that, like, let's say if you have a JSON-like structure or semi-structured data, and then there is no place for them for you to store them to get that optimization of where predicate push down that you would have on normal columns. But then you cannot create columns for each keys, because if you do that, the keys are very sparse. So sometimes those keys will have nulls, sometimes it won't. If you create columns for all of them, there will be like a 10,000 columns that you would be dealing with, and only 10 columns of that would get data at some point of time. They said
So
don't put it.
It allows you to put a key value map as a field, but you are also able to do
That's
this
right.
predicate push down, right? So
That's right. Yeah.
A lot of flexibility.
A lot of flexibility and not losing that latency sensitive workloads that you might have. So all these three things are more on a reader, making reader engine life much more easier. And moving in that direction, we see indexes, caching also getting enabled and available for Iceberg. Yeah, so we discussed the part of Iceberg V3, which is like very big changes that are coming up. Then there is like a lot of maintenance work also currently needed. So let's talk about them. So one of the major maintenance work is you will have a lot of small files for, let's say, for your very fast ingestion or streaming ingestion type of workloads. And dealing with small files in object storage is always painful, because it just do not have this data load. But for each data file, you will have manifest list, manifest files, a snapshot, and everything, right? So it does not stop that data. It just goes into the metadata bloating as well. And also, like this, the range that the file holds is very big enabler for efficient pruning, because it's a very small range that each file holds. Hence, pruning is also not that efficient. And if you have this Spark workloads, right, lot of files will create a lot of tasks. So these are like some pain points that you had with smaller files. Hence, rewriting them into bigger files is needed. Snapshot. Me and Ian have been discussing on this very cool feature of time travel, but then it comes with its own cost of snapshot management. You just do not need 10 years of data to be sitting there, and not just data, but their metadata as well, right? So you have to keep on expiring snapshots.
Yeah, and you might with with the tools that support this, you might get some some fancy logic where you get high frequency of the last 1 or 2 days maybe, but then with decreasing frequency over the past 30 days. Because you don't want to have this granularity for stuff.
Definitely. Yep. Yeah. So those things are there, and then engines will create. So let's say you are running a workload, and that got broken in between. So you have now data files with no metadata. There's no one referencing those data files. So those are orphan files. So you need to optimize your smaller files into bigger files, keep on expiring snapshots, delete orphan files. Your manifest files should also be rewritten to a bigger manifest files, things like that. And then there are different, like, new companies or new tools are even evolving to solve these things. So you have like S3 tables, which is specifically solving this. You have like we have me and Ian have been discussing on different open source alternatives that are coming, like 𝗵𝗵𝗶𝗃, 𝗪𝗵𝗵𝗵. There's also Apache Iceberg, I think, right?
Yeah, Apache Iceberg. And both projects have this, they have many different features, but the core responsibility here is to be able to manage and support the maintenance, right? And as I said, like one piece of mess is metadata bloat, another one is in the data plane, right? You need to compact this every now and then, and you need a tool that will that you'll be able to define your policies in.
And that there is a bigger problem also there. Like, so if you are using, let's say for data files, you want to compact smaller files to bigger files, you have to keep the whole Spark instance to do that. And 𝗵𝗵𝗶 actually plays there, where they say they have their local instance of Spark, so you don't have to set up a whole Spark cluster or like that. We need to set up. They just have this local instance, and that will do the stuff for you. So those things like are making a life easier for the people who maintain those tables, like especially the data engineers like us, is always beneficial, right? And that's on the open world, but in the managed world, like Databricks, so you have this liquid clustering, right? But then there are like a lot of knobs which are only enabled for your managed tables. If you want to do it for the external tables, you have to do it manually. Manually, I mean you have to run optimized table manually, and there's no predictive optimization as what they say, right? So yeah, that's there. Yeah. We can talk about processing engines. Processing engines. So there are 3 engines. There are many, but then let's focus on these 3 right now because they cover the whole breadth and depth. One Spark, the other is Trino, and then we have DuckDB. So Spark is majorly for your transforming or doing ETL type of workloads, because if you understand, right, so there's a lot of management that goes into bringing up the Spark cluster, right? The driver has to negotiate with your resource manager to get the executor and things like that. Hence, it is very helpful for your bigger workloads where you want to do ETL workload of transforming a data into specific gold layer, silver layer, stuff like that from your Lakehouse table. That's there. But if you are an analyst sitting and typing queries that select star or select count or whatever, right? You do not want the whole setup to happen, but you want instant results, right? There the Trino is there. So it has this, so the Spark has this architecture of driver and executor. Trino has this architecture of coordinator and executor. So driver at Spark need to provide its code distributed to all the workers. Coordinator do all the things by itself and just give simple instruction to the workers. So they do not need this code transfer or setting up different infrastructure. So for
analysts, you have like multiple threads, but a single process, right? So
that's right.
This is the most lightweight and very well fitting for like exploratory analysis for analysts, as you mentioned. But it is pretty performant for the resources it uses, but it also has a certain bottleneck. So not a great fit for huge pipelines running in the background.
Yeah. So like your night workload that you would want to process into your silver zone or whatever, don't use Trino. Trino, just use it for your query perform, like analytical queries or ad hoc queries. A DuckDB goes one step before that. If you're locally developing anything, it's a single process setup. Use DuckDB to just query those things. Not the whole iceberg table, but maybe a subset of it. Because it provides that. I think writer is still not available, but reader is available. Like scanning part is available by DuckDB. I think they're actively working on a writer. I think they're working on writer since 5 years, but it's still not yet available. But let's see. Maybe with the DuckLake that they're creating, that could be the part. Because of that, they are not building writer. Not sure. But yeah, so these are like the scanning part, the query processing part. Similar thing happen when you're writing the data, right? So Spark again do all the shuffling so that it get not that many small files. While your Trino, when you're trying to write, it's a streaming load, and it do all of the things in its memory. So they call it as pages, which comes into your memory, and then depending on fly, they divide into different partitions and then send to the data. It is susceptible to the small file size problems. While if you ingest the data through Spark ingestion, it is not. It's not that small size. But yeah, we can have like a dedicated session just to discuss the query engine. But on a high level, just to understand, like different workloads need different engines, and different ingestion patterns also need different engines on a high level.
And with Lakehouse, all of this is pluggable, right? You can use all of them and just use the one that you need for a given purpose and query the whatever table you need. Right, but all of them, I think that when DuckDB came to the scene, it was a surprise to many, like how large data sets you can process. But with Iceberg, you get this metadata, right? So you actually you execute a query to you read the metadata to find which actually data files you need to process. So with Iceberg, you always need a catalog, right? So maybe we can talk a little bit about how do this catalogs work and what types of catalogs.
Definitely, and this is one of the place which is currently very debating or a very hot debatable topics right now. So people think of like whosoever owns your catalog will own your most of the processing pipelines, as we discussed in our last episode with Alex as well, right? So, but on a high level, what catalogs? Why do we need catalogs, especially for Iceberg? We need catalogs to perform ACID transaction, and we'll discuss how that happens. But also track location of the current metadata file. The problem with the object storage is, especially that was there for S3 specifically, where they do not have if available, right? So what happens is, let's say this is a writer that is trying to write a new data file, right? So it just so there's a data folder and then there's a metadata folder. In data folder, just create a Parquet file, refresh our metadata, check for data conflicts, write new manifest files, commit the new metadata file, and then this Iceberg REST catalog will take care of updating the metadata file. So that's where, like, if you have multiple concurrent writers trying to commit their own writes, one writer will, let's say one writer finishes before then the other writer. The next writer will have to read the snapshot that was committed by the first writer and then make changes over it. So it gets blocked there. Again, restart those 2, 3, 4, and 5 steps, and then tries to commit it back again, right? So that's on a high level is what we do with this Iceberg REST catalog. So REST catalog, so as you see right in the image, REST catalog is not just important for your tracking the location of current metadata file, but also very important for the ACID transition, because that is where you do commit, atomic commit and swap, right? Of the metadata file, the recent snapshot that you would want to commit, right? So that's responsible there. Like there are different catalogs, different approaches of catalog. One is Hive, the other Nessie is there, which is like creating your whole data platform as a Git. You rebranch from that, make changes, again commit to the catalog. Then we have REST catalog. I think that's the direction that Iceberg is trying to move, which is your Polaris catalog. And then we also have platform-specific catalogs such as Glue and Unity catalog, right? I'll just maybe take a couple of seconds to explain especially REST catalog, because that is where I feel the Iceberg community is driving towards. So let's say there's a writer which is trying to insert into a DB log. There's a table that exists. throws this query to the query engine. The query engine will load that table db.logs from the Iceberg REST catalog, right? To load that, it will just say load my table db.logs. Iceberg REST catalog will talk to Iceberg REST server to get that table, to put a get request on that and get that table and db.logs. The REST server will return your v1, which is the current metadata JSON that it's storing, which will be returned to REST catalog, and then REST catalog will pass it to the query engine. Then the query engine will push the Parquet file into the cloud and will in memory create a v2 metadata.json, which is the new version of metadata that it want to commits it to the REST catalog, right? And then put a post request that I want to update this from v1 to v2. Then again, like as we discussed on the multiple concurrent writers trying to write at the same point, it will do some checks and then atomically swap that metadata with the new version of the metadata.
And what might be not be very intuitive here, it wasn't for me, so it took me a while to actually wrap my head around this, is that the data change is not a RESTful operation. The RESTful operation is the client retrieving the metadata file from the REST catalog, right? And then you do like using optimistic locking, you do, okay, I have this file, I want to make this change to it, but then the file might be outdated, right? And then the REST catalog will give you the information that you need to rethink your life.
That's right.
But
exactly
the huge benefit of this here is that before REST catalogs or without REST catalogs, you might have different clients implementing different things. But this is said that this system, this catalog implements this OpenAI specification, and then you have a schema. OpenAPI is by far the most adopted standard of REST calls. So every system speaks it, and it also this is something that Alex pointed out on the previous session, that this allows maybe a bit better iteration and innovation, because with a single language it's much clearer and much easier for different clients to catch up and implement new features. So this was not very intuitive to me on how the REST catalogs work, and my assumption in the beginning was something that DuckLake is doing, and DuckLake provided a pretty fresh approach, because Iceberg was created to handle this massive, gigantic workloads. But it has certain limitations or maybe trade-offs that it influences, right? Your metadata is files, and the client needs to manage the files. DuckLake, that was, I think, 2 months ago, it rose to the scene, proposed a new open table format, where you no longer have metadata as files. You have a very similar metadata, but not just the pointer to the current snapshot is in the relational database, but also the whole metadata management is managed in a database. And it is providing critical benefits because a relational database has much lower latency than object storage, and also provides much better consistency guarantees, right? It's much easier to implement transactions and transactional and optimistic operations on a relational database. It's been built for it. And you might think that, okay, but what about scalability? The thing is that most organizations will not reach the scalability limit for metadata, right? Iceberg came in the big data world, as it's not really called like this anymore too much, because everybody's working with massive volume. But the true volume is in the data plane, tons of Parquet files. And if you have a Parquet file that has hundreds of megabytes, you might have some metadata on top of it, but this is a fraction of it. So a relational database like Postgres can handle the metadata load up to a really, really high amount of volume on your data plane, because metadata volume is much smaller. And on top of this, because this is designed to be much simpler, you might have fewer metadata to manage with this approach. And what we like about this a lot is the simplicity, right? Because yes, it probably has a bottleneck, but it provides a very simple way to store data and manage structured data that open table formats have proposed. And also, it is the data plane. The biggest and most important part of it is it's just Parquet. So it's if you want to ingest this into Iceberg, you just need to generate Iceberg metadata, just scan these files. Yes, it's a one-time cost, but migration is possible. Maybe not super straightforward, but it's not complicated either. And so the way I see it is that you could call it a poor man's data lakehouse or table format. Yeah, but in a way that it's a great starting point. And who knows, maybe it will be enough. It might just as well be enough, especially if we get adoption, because right now in DuckLake, it doesn't have almost any adoption, I think. It is possible to migrate to Iceberg if you need to, which is great if you start with that. And if at some point, 1 or 3 years from now, you will discover that you actually want something even more scalable, because talking about scalability, the ceiling of volume here is still massive, right? So but with a multinational corporation spanning across many continents, you might reach this the ceiling at some point. You might need something more sophisticated. But it allows you to move great volume with simplicity, much easier to grasp than all of the Iceberg ecosystem, I think. It's a really fresh and interesting development in the data world. Something, Sachin, that you were also pretty passionate about is that it solves the small fire problem almost completely, right? Because you can, you have this issue of small Parquet files, which are a problem if you are working with object storage. But here you can just buffer them in your relational database and only produce actual bigger Parquet files once.
Definitely.
Once you have enough data. So we are very optimistic on DuckLake. Hopefully, we'll see significant adoption. Same with Paimon. With Paimon, it's on a different league already, but still not as talked about. But right now, you as far as we know, you can only work with DuckDB against DuckLake. Cool. So this is all that we have prepared for you today. Thank you very much for watching, for your time and effort. If you want to, the recordings from all sessions are available in our YouTube channel. If you want to get notified whenever we schedule a new episode, and we do this every 2 weeks, so at the same time. So, the organization page on LinkedIn, just follow it, and then we invite everyone that does. Once again, my name is 𝗪𝗸𝗫𝗁, and together with me, Sachin Tripathi, we are hosts of DATAPULSE. And on the next episode in 2 weeks, we'll be talking about the big and I guess a little misunderstood problem of data governance and everything that comes with it. It's not just security. So once again, thank you very much, and see you in 2 weeks. And stream. I said it before.